Okay, good evening. Welcome everybody to today's colloquium. But before getting to the colloquium, I want to announce that the next colloquium next week will be given by Ashwin Vishwanath from Harvard. And to some extent, it will be a continuation to what Vladan is talking today about. But I want to welcome Vladan to the colloquium today and introduce him briefly. Vladan is really well known for his diverse set of experiments he's doing. He actually obtained his PhD from together with Ted Hensch as his advisor in Munich, and then moved on to Stanford to work with Steve Chu, both Nobel laureates now, and obtained there an assistant professorship. And then apparently was doing so well, he got recruited to MIT to work there, and he's now a full professor there since 20 plus years. And what I really enjoy is that he does a variety of experiments in quantum optics, quantum many-body physics, atom-light interaction, also trapped ions, and precision metrology. So pretty much the whole suite of AMO experiments, and all of his experiments are actually really interesting. And so, for instance, he did experiments on friction, and then at the same time doing also experiments, how does light interact with matter and entangling thousands of atoms with each other. And so we are really proud to have him here speaking about one of the topics he recently got involved with, and that is controlling many atoms at the individual level for quantum information applications. And probably he will mostly focus on the quantum many-body aspect today, but there are also prospects for computing. So please, Vladan, it's a pleasure to have you here.
Thank you very much for the very kind and very generous introduction. I would like to tell you today about experiments performed in collaboration with my colleagues and friends, Misha Lukin and Markus Greiner at Harvard University. And the title of my talk is The Quantum Age, from Bell Pairs to Quantum Computers, or in another way, how entanglement went from a spooky, strange phenomenon to a useful tool. So I would like to tell you a little bit to set the stage about entangled photons, which were really the first particles in some sense that were entangled. And Bell Pairs was created. And of course, this story is also tied to Berkeley in a very fundamental way. And then I would like to tell you about what you can think of as applications of entanglement, namely quantum simulation and quantum computation with arrays of individually controlled atoms and Rydberg interactions to make them interact on demand. Most of you have probably heard about the famous Einstein-Podolsky-Rosen, what Einstein called a paradox, namely this idea that I can take two particles and that I can make correlated states or entangled states with correlations that are somehow stronger than classical correlations. And what Einstein was unhappy about is that you could make, for instance, a sort of two particles, and you could arrange a situation in such a way that for each individual particle, say the position of the particle was uncertain as well as the momentum was uncertain, and the same for the second particle. But if you measured correlations between the two particles and you measured, for instance, a certain position here in x, then you could conclude what the position of the first particle would be. And similarly, you could instead choose to measure momentum of the second particle and then infer information about the first particle. And Einstein really was unhappy about that. He says, physical reality can predict of the outcome of the measurements with certainty. How is it possible that one cannot know the position or momentum of the particle, but one can have these in local measurements, but one can make measurements on a particle far away and learn something about the first particle. I looked up this citation maybe 2 years ago. It's even more extreme now, so let's start from down here. These are his top 5 papers. This is his work on gravitational waves. It's number 5 on the top 10 list. And then elektrodynamic bewegter Körper. That's really special relativity here. So he's special relativity theory is number 4. This is Brownian motion here, number 3. This is the photoelectric effect über die Erzeugung und Verwandlung des Lichtes betreffend den heuristischen Gesichtspunkt. So that's photoelectric effect. That's what he got the Nobel Prize for. But by far his most cited work is this Einstein-Podolsky-Rosen paradox: can quantum mechanical description of physical reality be considered complete? And you see it's, by now, this was 2 years ago, it's even more highly cited than all the other paper, a paper that you could argue is maybe wrong or takes at least the wrong viewpoint, as opposed to the other papers. And it's really this explosion of studies of experimental, both theoretical and experimental, about entanglement and quantum mechanics that have propelled this to his bestseller. Apparently, he also didn't verify his email address. But already in classical problems, you can ask yourself, where does information really reside? Let's imagine a box with a white and the black ball, and you shake it, and then you share. One ball goes to Bob, one ball goes to Alice. And as soon as Alice learns the color of her ball, that it's white, she knows immediately that Bob must have a black ball, right? Even though they could, in principle, be over large distances apart. So there's already the question, is the information everywhere? Is it somehow in the middle? Is it delocalized? What does it mean? And this gets even sharper when we take the version of this experiment in quantum mechanical terms, where instead of the color of the ball, we have now 2 levels that we either traditionally call a spin 1/2 system with 2 levels, or in more modern quantum processing language, we think of this as a so-called quantum bit, with one state being labeled 0 and the other state being labeled 1. And then it turns out quantum mechanically, of course, because you don't have to be in either 0 or 1, but you can be in a superposition state. This object here, this quantum bit, is richer than in classical physics. And one good way to describe it or think about the system is on a unit sphere, where the direction determines or is directly associated with the qubit. So we can label, for instance, the up state when this spin is pointing along the plus z direction as 0, the down state as 1, and then any state along this equator here would be an equal superposition of these 2 states with a phase that is associated with the direction along the x minus x plus or minus y axis. And so this is a complete mapping of this qubit onto this sphere. And as you see in quantum mechanics, instead of having just 2 possibilities classically, I have all these sphere states. It becomes now more interesting if we consider the EPR paradox in a spin system, as Bell did. So we now have 2 particles, and instead of considering momentum and position, we can consider the spin of the particle. And I can now choose to measure along different bases, along different directions. And what is characteristic is about quantum mechanical spin is that no matter which direction I choose to measure on, I always get only 2 possible outcomes. The outcomes are digitized. And so what Bell figured out is that one could, if you want, experimentally test Einstein's paradox by looking at certain correlations between these 2 objects. And if Einstein's viewpoint was correct, then a certain combinations of measurements or expectation values of correlations would classically be less or equal than 2, and quantum mechanically it could take up a value up to 2 root 2. And this is the famous Bell inequality that says if Einstein's viewpoint was right, this would be measured, but quantum mechanically we can measure a larger number for these correlations. And then states that maximally violate this inequality are called Bell states today. And the particularly interesting Bell state is, for instance, one that is where the particles are anti-correlated on every basis. So you can write down the quantum mechanical states, which says if I measure 0 for the first particle, I measure 1 for the second particle along the same axis, or if I measure 1 for the first particle, I always measure 0 for the second particle. And this state, you can convince yourself when you transform it, is actually the same, has the same form along any basis. So quantum mechanically, I can make these measurements. So this would be one of the 4 Bell states. And of course, you may know that the Nobel Prize now 2 years ago was given for experimentally verifying that the Bell inequality is broken by quantum mechanical states. And the first to do this type of measurements was your own John Clauser here, who did measurements in 72 and 74 in a slightly different form. He came up with different inequalities, but they were testing the same thing. And you can ask yourself, how do I make entangled photons? Isn't this very hard? How do I make entanglement? It turns out that a simple way to do this is to take an atom with a specific structure that you take in an excited state. And this specific structure is that you have some total angular momentum of 0 in the excited state, and you take the magnetic sublevel, so MF, the M quantum number also has to be 0. And this atom has now 2 decay paths. It can either emit a right circularly polarized photon, sigma plus, of a certain color, and then a sigma minus photon of a different color. And because angular momentum is conserved as it takes this path, this photon has to have +1 of angular momentum, and this photon has to -1 h bar of angular momentum. But it also can take the opposing path. First a red sigma minus photon, and then a blue sigma plus photon. And this decay by itself entangles the red photon and the blue photon. You can kind of see that whenever the red photon is sigma plus, the blue photon is sigma minus, and vice versa. So this decay creates automatically one of the Bell states, and that's how these measurements were performed. This is the actual level scheme. Alain Aspect took this then a little bit further. He now also used basically measurements that were far enough away so that he could measure in different bases so quickly that there was no way for classical communication between this polarizer setting and that polarizer setting. So he also looked at correlations on time scales where basically it was impossible for the information to travel. And he was the second Nobel Prize recipient, and then Anton Zeilinger was the first one. He did a few, I would say, stunt experiments. One of them is he used photons from different galaxies to set his polarizers axis randomly with the argument that these photons had never spoken to one another because they came from different parts of the universe, for instance. He also invented a more efficient way, rather than atoms, to make these entangled photons. Basically, you have a high energy photon that breaks up into 2 lower energy photon ones in certain types of nonlinear crystals that you can use to make entangled states. And he also did the first experiment on so-called quantum teleportation, where you have one entangled pair of photons that interact with one another, another entangled pair, they interact with one another, and then you make a joint measurement on this middle pair, and you manage to entangle photons that had never seen each other. Right? These photons had never interacted with one another. It's kind of, you can teleport this entanglement. So this is very interesting. And these photonic experiments were beautiful in the first ones, but they are hard to scale because photons have losses and you can only make individual pairs. It's hard to see, even though some places are trying to make very large entangled states of photons. So here we switch to atoms. And photons are ideal carriers of quantum information. But as I said, losses make it difficult to create states with large photon number on demand. Atoms are more difficult to control initially because at room temperature they're flying at high velocities through this room. But once you laser cool them down and trap them, then you can control them and they can have strong interactions, as I will show you. And quantum states can be stored for long times. So record quantum state storage in atoms or ions is now on the 30-minute time scale, so half an hour or so you can store quantum information in principle in the best systems. So, and then this brings us to a situation where we no longer study entanglement, but we actually try to use it or to see where in nature and many body systems it plays a role and what role it plays. And one of these areas that has emerged is the so-called quantum simulation and computation, where the simulation aspect is we think more of an analog evolution of a large many-body system, and then the computation aspect we think more of a kind of digital gate-based approach. That's one way to think about these. And this brings me to a remarkable quote by Richard Feynman from 1983, so now 40 years ago, where he said the following: "Now we can, in principle, make a computing device in which the numbers are represented by a row of atoms, with each atom in either of the 2 states. That's our input. Then the Hamiltonian starts. The ones move around, the zeros move around. Finally, a particular bunch of atoms represents the answer. Nothing could be made smaller, nothing can be made more elegant." And I will a little bit later show you movies where I'm surprised myself, how close or how Richard Feynman guessed this. We are, having systems where we can move the atoms around, where they represent ones and zeros, and where we can read them out, everything optically. So let me tell you how to control individual atoms. This goes back to a now famous paper by Philippe Grangier and colleagues in Paris in 2001, where maybe at the time its significance wasn't quite realized, although it was a well-known paper. So at that time, people had, Steve Choof had invented laser cooling, and people knew how to cool and trap atoms, bring them using laser light to very low temperatures, maybe microkelvin above absolute zero. And people also knew how to trap atoms in laser beam. Basically, an atom is like a polarizable particle, and you've put in a laser beam. You can trap atoms if the laser beam is at a lower frequency than any atomic transition of relevance. So the thing that made Philippe Grangier's experiment differently is he said, let me see what happens if I try to trap atoms in a tight optical trap that I can make. So he took a laser beam, a very good microscope objective lens, and he focused the laser beam down to the diffraction limit of about 0.8 nanometers. So the tightest that you can focus light because of diffraction. And then he laser cooled atoms in this regime, and this was a trap, and he looked what happened to the trap, like how many atoms does it trap. And that was done simply by imaging the light emitted by the atoms, scattered by the atoms, back through the objective onto a CCD camera. So that's a method still used. And he saw these remarkable traces where he saw for long periods of time, this is a time in seconds, two different values of the signal. This lower value here is basically the trap is empty. It has non-zero counts. This is a photon counter here you can think of. Has non-zero counts because simply there's background scattering into the camera a little bit and so on. So you see this is an empty trap. And then he saw, this is one atom. He saw this kind of telegraph digitized signal. Right? And so what is this fluorescence level here corresponds to one atom. And what is conspicuously absent is two or more atoms. You would think that loading atoms into a trap is a Poissonian process, so you should see sometimes two, some more rarely three atoms, etc. But he never saw that. And then he already understood when analyzing these results that what was happening. The trap was so tight that when two atoms were inside this trap, they were at a distance roughly on a wavelength or less. When they were excited by the laser cooling light, they would be excited to a molecular state and then decay to a molecular state. It would become invisible and also fall just out of the trap. So basically, you can think of this, there are sharp spikes on top of this here where two atoms are briefly in the trap and then both are lost. And when both are lost, then you go back to zero. And that explains why about half of the time he saw one atom in the trap and half of the time there were no atoms. Whenever a second atom joined, the atoms were gone. Now this is hard to scale, right? Because if you have only an atom half the time in the system, right, and you want to scale it to 10 atoms, your probability is 1/2 to the power 10. So it's exponentially bad to make large systems. At that time, in collaboration with Misha and Markus, we thought of trying something which had been around. It wasn't really our idea. I don't know whether anybody invented this or it came out through discussions, but people didn't really think that it was going to work very well. So that's, I guess, why nobody tried. But the idea was, well, if we can image the atoms and know which traps are filled, then we can just kind of have a computer look at the camera image, decide which traps are filled, and rearrange the traps to quasi-deterministically trap atoms. So what we did is instead of having a single laser beam here, we used the so-called acousto-optic deflector that can, in this case, make up to 100 traps or so. So instead of one trap, we have now 100 traps. We focus them through a microscope objective into this vacuum cell where we laser cool atoms. And then on the other side, we look at the atoms of the camera. And then some traps will be randomly filled and others won't. But the computer can look at the CCD image and then rearrange the traps. It can turn off the empty traps and rearrange by moving the frequencies here. Basically, these laser beams are controlled by radio frequencies into this device. It can move the traps around and can reconfigure them. And so this is what we saw. I'll show you a movie that is a little bit slowed down. So here, I don't know whether it's bright enough here. You see a 1D row. These are about 100 traps. And then the white spots are individual atoms. What you're seeing here is an image of an individual atom. And this movie, which should be playing, will be slowed down by a factor of a few. And so you see that we rearrange then the traps, or rather the computer does, to make an almost deterministic string of atoms. Sometimes an atom is lost during the process. This takes about 100 milliseconds or so each time. So now we can make strings of atoms, in this case in one dimension. Tens of atoms. So in 1D, for instance, this is an arbitrary loaded string. We can arrange them into long strings by turning off the empty traps and moving the filled traps over, or we can arrange them in pairs of two or some longer strings, etc. So quickly, we and also Antoine Bravo's group in Paris, who was a pioneer in this, did this also for 2D systems. So we are sorting these atoms randomly now into a 2D array. Here you can see about 200 atoms or so, and these are the leftover atoms from the sorting process. And in this system, we could achieve about 98 at the time, 98% filling fraction for a few hundred traps or so. In this case, I think it was 225 traps. And then Antoine Brouvet's group, our colleagues in Paris, they even did three-dimensional structure. You can see where they come from here. They did even Eiffel Tower, and then some of this is a torus. This is, I think, this is a fullerene-like. This is a torus. This is a cone, etc. So one can also do 3D structures. We like 2D structures, actually, because it gives us the third dimension to access the atoms and address the atoms with a laser beam without having to go through other layers of atoms that would be potentially disturbed. So we really work in 2D, but in principle, it's possible in 3D as well. And just to give you an idea of the scale is such that we can place the atoms at distances of a few micrometers from one another. So basically, on a crossed human hair, you can fit something like 10,000 atoms or so. OK, so now we can make individual deterministic atoms, but we can't entangle them yet, right? Because atoms in the ground state, they are kind of a few micrometer distances from one another. They're just not talking to one another. For entanglement and interesting states, you need interactions. So also now 20 years ago, Misha Lukin, together with Dieter Jaksch, Ignacio Sirac, Peter Zoller, and Steve Rolston, and Robin Coté came up with an idea that seemed very crazy at the time, how to make atoms interact over long distances. He says what you should be doing is you take an atom from the ground, electronic ground state, and excite it to a very high lying state, a so-called Rydberg state. Think of hydrogen with principal quantum number n equals 100. Okay? So crazy state. In these states, the electrons are very far from the nucleus, and therefore the atoms are very polarizable. And then basically small quantum fluctuations in one atom in such an excited state will polarize, will pull the electron in the other atom, and will make very, very strong interactions. So Rydberg states were first studied by Johannes Rydberg, and this is a typical, say, wave function for what an S state would look like for n equals 35. So they have a lot of probability on the outside, far away from the nucleus. For instance, the atoms we work with, the distance of the electron from the nucleus is about 1 micrometer. To realize how big that is, you could take a whole COVID virus and put it inside the atom, and it would fit. Okay, so it's really macroscopic, right? Very large. These were first studies in spectroscopic precision context by my MIT colleague Dan Kleppner, and of course Serge Haroche used these interactions in the microwave domain, not in the optical domain, for his Nobel Prize work on also entanglement. So the idea is that you have these atoms where the electron is very far away from the nucleus, and so they're very polarizable, and therefore they can interact over distances of typically a few micrometers or 10 micrometers. The interaction, depending on the level, is so strong that it can give rise to shifts even at these distances of a few hundred megahertz. It scales very, very strongly with the principal quantum number as the 11th power, and so if you go to n equals 100, you have enormous interactions. And then one way to think about these systems is the following. We define some kind of characteristic radius, which we call blockade radius, and if the atoms are further apart from the blockade radius, they don't seem much of each other. So you can excite this atom to the Rydberg state and simultaneously this atom to the Rydberg state. The interaction between two atoms is a van der Waals interaction. It's basically quantum fluctuations in one atom polarize the other atom, so it's a 1 over r to the 6, very strong distance dependence. So if the atoms are 10, 20 microns apart, they almost don't see each other. On the other hand, if they are closer than a characteristic distance because of this 1 over r to the 6 potential, then if you excite the first atom, it will take a very different energy to excite the second atom to the Rydberg state because of the strong Rydberg-Rydberg interaction, whereas Rydberg-ground interaction is negligible. So in this case, basically, if you excite the first atom, the second atom would not be excited, but of course the system is symmetric. If you excite the second atom, the first atom would not be excited. So what happens here? Well, automatically, if you try to drive this two-atom system, a Bell state is formed because you have either the left atom excited or the right atom excited, and they're both in a superposition because I'm driving them with the same laser beam. And so one can immediately see kind of these quantum gate or Bell state-like parity oscillations where, depending on which basis I'm looking at, I'm either exciting only one atom or only other atom, but never both, or I can look at other correlations. And so you can immediately use this to do so-called 2-qubit quantum gates, which are the quantum generalization of Boolean logical gates for classical bits, just by using this Rydberg interaction. And the nice thing about this is it doesn't really matter how far this Rydberg state is shifted. As long as it's shifted far, you don't care about its value. So you're not very, very sensitive to the exact parameters of the system. You just need to make the energy shift large enough. And so now this has been, experiments are going on in many, many places. This field has kind of taken off. There's probably more than 60 experiments now around the world trying to use these to study both quantum many-body states and also potentially quantum computing. So these are the two ingredients. Let me tell you a little bit about experiments on the analog side of things that you can do as quantum simulation. One of the first experiments that we started is we built in 1D an array of up to 51 atoms. And then we tried to excite all the atoms simultaneously to the state. But because the atoms are interacting strongly with one another, if you excite atom number 1, you can't excite atom number 2. But then you can excite, again, atom number 3, etc. So you get to a situation where you get these, if you want, antiferromagnetic correlations, right? One atom is excited, the next one is in the ground state, the third atom is excited. At the time, we had a coherence length of about 6 atoms or so. These were in first experiments. So basically, you think of this is an antiferromagnet and then some kind of spin domain and then another antiferromagnetic. But you see very strong antiferromagnetic correlations in this 1D system. We then generalize this to 2D. So here we load a random 2D lattice. As I've shown you, we rearrange the atoms, for instance, into a square lattice. And then we try again to apply this laser beam to drive all atoms globally to the Rydberg state. And then what you see is this beautiful now 2D pattern emerges where the circles indicate missing atoms. The way we detect atoms is we push the Rydberg atoms out of the system. So any atom that was in a Rydberg state is now missing atoms, and the ground state atoms are imaged by fluorescence. All addressing and all imaging here is purely optical. You shine light on it, and then you image the atoms. So you see these antiferromagnetic patterns in 2D, but one can also do more interesting geometries that have maybe spin frustration, hexagonal geometries, triangular geometries, etc. So this showed that this system is robust, and here basically our correlation length increased. In this case, we had 15 by 15 atoms in this system, and our correlation length was 11 atoms. So this means almost the whole array is actually one spin domain or one antiferromagnetic domain. So it got a lot better. And then you can study, for instance, what you can do now is you can vary the spacing of the atoms relative to this blockade. So here the atoms are relatively far. So one atom in the Rydberg state only blocks its four nearest neighbors. And so you get this kind of pattern for the ground state. But then if you either increase the Rydberg radius by going to higher n level, higher interactions, or you space the atoms more closely, now the atom blocks not only its 4 direct next neighbors, but also the atoms on the diagonal. And then in this case, you get different ordering. And then if you block even more than the next neighbors, you get these striped kind of ordering. So there's a lot of interesting, at least ground state physics in these systems just coming from these interactions. So these were all predicted. One thing that surprised us, and maybe the only surprise really coming out of the system so far, is what people now call quantum many-body scars. So what we tried to do in this experiment is we tried to make an antiferromagnetic order. And the way we do it adiabatically. So basically what we do is we start with all atoms in the ground state. This is showing you 9 atoms as a function of time. Dark means ground state, bright means excited state, colored means excited state. We start with all these atoms in the ground state, and what we do is then we turn on our laser beam and slowly tune the laser beam through resonance. And that should adiabatically prepare this antiferromagnetic state. And as you can see here, it does. So we have this antiferromagnetic order where the first atom is in the Rydberg state, ground, Rydberg, ground, etc. And then what we were trying to do is we were trying to look for thermalization. We said, let's quench the system. Let's jump directly onto resonance and let's see how long the system takes to go to some random states, right? And we expected some exponential decay of this ordering in the system. But instead, what we saw to our surprise is that this ordering, well, it quickly decayed to something where all the atoms seem to be in the ground state, but then the ordering recovered. However, now what had been a Rydberg atom is now a ground state, and what had been a ground state atom had been a Rydberg state. So it's kind of switched to the opposite antiferromagnetic order. And then it, after a period, it switched back to the original ordering and so on. We saw these persistent oscillations. This is very surprising because, you're quenching the systems. These are 2 to the 11th state in the system, so a large number of states, and yet you see this kind of, interesting dynamics in the system after a quench. It's now believed to be or understood to be a situation where you have many similar states. This is not just one quantum state, but many states of similar energy being grouped together with the same kind of properties. But it's still remarkable because you see here almost all the atoms are in the ground state, but somehow the system remembers that it should go to this order and not to the original order. And then afterwards it remembers again that it should go to the antiferromagnetic ordering. And we saw this not only in 1D and not only with 9 atoms, but when we did the same thing with 51 atoms in 1D, it looked essentially the same period, etc. You can make a very simple model, and you predict a root 2 kind of, 2-particle model, a root 2 dependency, but the observed frequency, oscillation frequency was different, but it was explained by this quantum many-body scarce model by by various theoretical work, including this one. We then looked at this phenomenon not only in 1D chains, but also in 2D, and we found that it was ubiquitous. For instance, we saw it in a square lattice, in a honeycomb lattice, in a leap lattice, in some other types of lattices. In every one of these lattices, when we made an antiferromagnetic ground state adiabatically and then quenched the system, we saw these kind of persistent oscillations for a while. So it seems some kind of surprising, very generic many-body phenomenon and situation rather than what you would expect, just some kind of exponential type of thermalization in the system. We understood that these systems are getting bigger and bigger and harder and harder in control. So already a number of years ago, we founded actually a company that is supposed to engineer these better systems, Quera, and it's a Boston-based startup. And for instance, since 2022, it's actually possible to access this analog system for now via AWS. So we have theorists who do actually their final experiment on this machine to test some of their proposed systems. So this was kind of some of the analog side. I would like to now switch gears and tell you a little bit about the digital side, digital quantum machines. And so here, just for the non-expert, I would like briefly to introduce quantum gates. So with classical bits, we have Boolean gates and AND gates, OR gates, and you can use them to perform computation. There's a generalization of this for quantum bits where you can, for instance, a famous example is the C0 gate, where you can specify the input state of 2 qubits and then the output state of 2 qubits. In this particular controlled NOT gate, what it does is if the first control atom or control bit is in state 0, then the state of the second atom remains unchanged. But if the state of the control bit is in 1, then the state of the second atom gets flipped. And so you can see, for instance, that if you have a C0 gate and you start out of a superposition with an unentangled state, where the first atom is in a superposition of states and the second atom is in the ground state, then after applying the C0 gate, you automatically make this Bell states, one of these interesting Bell states. So basically, once you had this together with some single particle gates, you have universal quantum computation. Now, quantum systems are very prone to errors, and many people believe, and maybe many still believe, that it will never be possible to make very large quantum systems containing hundreds, thousands, tens of thousands of qubits because of inevitable decay. Something that I find amazing is that even as a quantum person, that one can, even in the quantum domain, correct errors. Of course, in the classical domains, we know how to correct errors. If we have a classical bit and it's somehow prone to some flips, what we do is we encode it redundantly into a number of copies, and then we rely just on the fact that if we take in the end a majority vote and 2 of the atoms flipped, it is much more likely that 2 of the atoms flipped and that the white state is the true state than that, in this case, 7 of the atoms flipped and the red state is the true state. And as you make this chain longer and longer, you suppress errors, or at least uncorrelated errors, exponentially, right? And this is how you encode things classically. The problem for quantum bits is, of course, you're not allowed to look at the qubits, right? Because as soon as you look at the qubits to see which state they are in, the quantum system is destroyed. So I find it remarkable that it's actually possible to come up with schemes that even though you're not allowed to look at the qubits, you can actually detect errors by redundant decoding. And one example that I will show you here is a famous example. It's a so-called surface code. It's a 2D code where half of your bits are the computation qubits shown as white circles. And then the other half of your qubits are ancilla or helper qubits that help you detect errors in this device. And if you take an ancilla qubit and make it perform 4, say, C0 quantum gates with 4 neighboring data qubits, then this ancilla qubit will measure whether all 4 are in the same state or whether one of them is in a different state, regardless of what state the data qubits are in. So it doesn't reveal the state of the data qubits, but it reveals, if you want, the parity of the system. Are they all in the same state, or are 3 of them in the same state and one is in a different state? And so, for instance, if this data qubit here has an error, then the 4 ancilla qubits around it, in the simplest way, will light up and tell you that the error occurred here in the simplest example, nowhere else. So it's remarkable that you can use extra qubits that you can then measure to detect errors in your data qubits, and then you can localize them and correct them. In practice, of course, if you have more than one error, this becomes much more complicated, and even the decoding problem, given what ancilla qubits lighted up, what is the most likely state or the most likely error or errors that occurred is actually a hard problem to do. But it can be done, and this is kind of the basic idea. Now, because you have to perform these additional gates here, right, compared to just normal quantum computing, you're performing extra gates to detect any errors, there's actually an overhead. And these gates themselves that are used to detect the errors could have errors, right? So it turns out that there's a price to pay, obviously, and there's a threshold for the system. If your native quantum gates are not good enough, then basically as you make the system larger and larger, the system gets worse and worse, okay, because you're just making too many errors trying to detect errors. However, if your native gates are below a certain threshold, and the surface code is famous because that threshold is relatively high, 1% error, if your native gates are below that threshold, then actually as you make the system larger redundancy, the system actually gets exponentially better, right? So there's this concept of the threshold that you need to meet for your physical qubit gates. So let me tell you a little bit about how we characterize the gates. So you need single qubit gates. These are basically just rotations of the qubits with a laser beam and 2 qubit gates. Contrary to what I've shown you, we encode the information into electronic ground states for the expert's hyperfine ground states that are magnetic field insensitive, 0 and 1. And here the coherence can live for a long time, tens of seconds. Whereas when we want to make the atoms interact, we very briefly, maybe on the order of a few hundred nanoseconds, put them in a Rydberg state, because this state has a lot of more decay, just to execute the gate, and then we bring the qubit back down. So it's really a free-level system where we store quantum information here, and then whenever we want to make gates, we briefly put atoms into this Rydberg state. And so first we study how well can we rotate the single qubit, and by now we can do many, many rotations shown here as Rabi flopping, and the errors are 2 times 10 to the minus 4. So the single qubit errors are well below the surface code threshold of 1%. We think this is for now solved, right? Then, more importantly, are 2 qubit gates. I showed you this graph before. How well can we make those? Those are harder to make because these involve really exciting the atoms to the Rydberg gate. We worked hard on this, and we now achieved an infidelity of about 0.5% for 2 Rydberg qubit gates. So why is this important? It's below this threshold of 1% for the surface code. So we are in a regime where, in principle, we should now be in a place where we can start, and as I will show you, we do start to do error correction on these systems. Yeah, this is another. We can do this not only on 1 pair of atoms, but actually on up to 30 pairs of atoms, so we can make it for large systems. And then another thing that became very important is that we can not only entangle atoms, but after entangling them, making a Bell state in the spin basis, we can also move the laser beams around to transport the atoms to distances of maybe hundreds of micrometers, and then bring them back to test, are they still entangled? And if we do it correctly, we see no decay from the transport itself. So that means we can not only entangle next neighbors, but we can entangle next neighbors and then bring the atoms somewhere else to entangle with other atoms so that we don't have to propagate entanglement step by step through the system, but actually over large distances. And we think this is a very important feature. So I'll show you now a so-called toric code. So this is an error code similar to the surface code, except it lives effectively on the surface of a torus. And because we can move the atoms around, we can make, even with 2D system, any dimensionality. We can do 3D, 4D, 5D dimensional codes in principle. So I'll show you this where we have data qubits and ancilla qubits. The ancilla qubits are going to interact with the data qubits, and then finally measure out the ancilla qubits and see whether they detect. We also measure the data qubits and to check whether they detect the correct errors. So this is what the movie looks like. We actually here move the data qubits for simplicity and leave the ancilla qubits in the fixed place. And whenever a red circle appears, that's when we do a quantum gate. So we start out with a quantum gate between one ancilla and one data qubit. And then this system moves around. So this is a second Rydberg gate, a third Rydberg gate, a fourth Rydberg gate, and then one all the way around. This is to close kind of around the torus. And then finally, we transport the data qubits into a different region. And then we measure the ancilla qubits here and check whether they show the errors of the data qubits. And at some reasonable level, we could see in the system already that these ancilla qubits correctly identify the errors of the data qubits. What we haven't done yet is put this into a closed feedback loop, right? What you would want to do is read these ancilla qubits and then either make a note or use a laser to flip the data qubit that had an error, and then do this many, many times around. So close the feedback loop many times. So this is kind of a geometry, and this was a simpler geometry from a paper where we have at least 2 zones. Right now we're thinking of 3 and 4 zones. One, the computation zone where we perform the quantum gates, and another zone where we read out the state of the ancilla qubits, and then there will be at least one more zone where we have, a reservoir of atoms that we can refill as sometimes atoms get lost from the system. So now I will show you finally, to wrap up, some experiments with, first experiment for logical qubits. We have done up to 10 logical qubits. What we mean by that is these are qubits where we use redundant encoding and then some kind of ancilla readout to detect errors or correct errors. And error detection can increase fidelity, but this is really a work in progress. We think this just barely opens the door a little bit into this regime of experiments with logical qubits or error-corrected quantum systems. So in this example, I will show you something where we used 10 logical qubits, each consisting of 7 physical qubits. For the expert, this is the Steen code, where we basically are trying to prepare a so-called GHZ state or maximally entangled states of 5 logical qubits. A maximally entangled state is all 5 qubits up plus all 5 qubits down in a coherent superposition. So these are kind of maximally, or in some sense, the hardest to make states because they decohere the fastest. And we do this with error detection by using the other 5 logical qubits to detect any errors in the preparation of these first qubits, and then we perform the gates used to create the GHZ state. And so this is what it looks like. You see here atoms in groups of 7. So each one of these is a logical qubit, and then we will move them around. And what you will see is we can make these things move in parallel. So we can do so-called transverse gates where the whole group of these atoms, each one interacts with exactly one partner over here. So let me show you the movie. Now I don't have the red. So whenever the atoms stop, there's a Rydberg gate. There was another Rydberg gate. Now there's a second set of Rydberg gates. Now we separated the ancilla qubits from the data qubits, and then we're performing the rest of the C0 gates on the logical qubits over here. Right. So this gives you an idea of what we can do. And sorry, I don't have the data here. For some reason, it doesn't show up. But basically, what we do is if we look at the errors, if these indicate errors that have happened, and we only keep the instances where no errors were detected, then we find that we have a perfectly created 5-atom GHZ state. And finally, the most complicated code we have done so far. In this case, we have 12 logical qubits, and each logical qubit is encoded on this hypercube, this kind of 8-atom, 8 physical qubit systems. And then we again perform some circuit between them, which is hard to sample classically. So let me show you the movie. Again, there are no red circles, but each time two atoms come close, a Rydberg gate is performed. We perform some complicated circuit with this group of atoms. And then we now transport them in the other region, perform some other logical qubit operations in the system. So what you see is there's a high degree of parallelism in the system. When we originally set this up, we thought maybe we have to control each atom individually, and that would be very expensive, right? Because we would need one or more control channels per physical qubits. But as you see, a lot of these gates, these are only Clifford gates for the experts, can be done in parallel, where we transport a whole group of atoms so that we have only one control channel per logical qubit rather than per physical qubit. Okay, so to wrap up my talk, let me try to make some predictions, and I may be wrong. This is a speculative field, but let me tell you where I think we are and where we will be. The entanglement is transforming from a surprising, disturbing, according to Einstein, concept into a useful tool in systems. Large-scale entanglement is now experimentally possible. And by large scale, I mean, we have done up to a few hundred qubits. Manuel Ender's group in Caltech, they haven't yet entangled, but they have created systems with 1,000 qubits. I think we are well on our path to make systems with 10,000 to 100,000 physical qubits within the next 1 to 2 years in these kind of systems. Quantum simulators are already useful for science, so where we use these systems to study other quantum systems. Quantum error correction seems feasible. We have to still close the feedback loop, but I predict that with these kind of physical qubits numbers, we'll have 10 to 100 logical qubits in 2 years' time or so, with errors of 10 to the minus 5 and 10 to the minus 6. To solve, say, Shor's famous algorithm and break, the RSA code, to be better than a supercomputer, we would need a few thousand logical qubits at error rates of 10 to minus 12, just to give you a scale. But of course, once we are on this, we are on in principle an exponential scale by making systems larger. What we really don't know is, we know it's useful for simulating quantum science, but are there algorithms beyond Shor's algorithm that are useful for solving classical computer problems that are of value to us, right? Is it possible to solve some other classical problems with quantum computers? And that's really very much an open question at this point. Our approach to this is many algorithms have been proposed, but except for Shor's algorithm, we don't have proofs of exponential speedup. We try to build a quantum system that is large enough that we can explore the scaling. That means probably on the order of 100 or so logical qubits, that we can see how these systems, how the runtime and the error scale with system size. And so that's, I think, where we are, and I thank you for your attention.
Thank you very much, Vladan, for this fantastic talk and giving us insights into what the future may hold. The floor is open for questions.
What sets this 10,000 to 100,000 number of prediction? Don't you run into issues like the field of view of your objective just being small?
Exactly, that's part of it. So right now we have objectives with about 1.5 millimeter across. So the typical spacing is down to 3 microns. So there we can fit 100,000 atoms or more in it. One limit is laser power. For the traps, we need about 1 milliwatt per trap. So we're talking at 100,000 traps, we're talking about a 100-watt laser. And also, objectives are used for collecting light. They are not meant to send 100-watt laser beams through them and not have them heat up. So there are some practical issues. In principle, larger field of use can be designed. My ever optimistic friend Misha Lukin likes to point out that in the semiconductor industry, they have 1 foot or so, or I don't know how big, wafers, which are, with tens of nanometer of resolution. So the optical problem can be solved, in combination with the laser power, the heating expansion. We don't know. That's why I put the number here at 100,000. So that's a 100-watt laser, currently available microscope objectives, assuming that we control thermal effects in the system.
quantum star. So what ended up saying that well-defined energy scale?
Yeah, it's roughly the Rydberg interaction energy between two neighboring atoms, but it has a numerical factor in front. A numerical factor in front that comes from many-body calculations. So the scale itself is just the interaction energy.
Same on the many-body star. Do you see like a different behavior when you have like say Z2 symmetry breaking and then you have like even on all sides of number of atoms?
So yeah. So very good question. Most experiments that we have done has an odd number of atoms because the ground state is unique. You excite the Rydberg atoms. We have done only 1 or 2 experiments of even sites of atoms because you have doubly degenerate atoms. We used it to prepare a GHZ state, but we haven't studied quantum cars in this regime because it's just hard to prepare a single state in the system. But it's a very good question.
So, in there it says you want to, in the next 2 years, want to go to more kind of logical qubits error to 25 and 6. Does this, like, which direction you want to push on? Do you want to just increase the size of the atom array, or you want to push on go to qubit gate?
All of the, all of the above. I mean, the idea is these errors you can reach if you can say have 99.8% physical qubit fidelity, then you need about 200 physical qubits per logical qubit, right? And then that's where the numbers come. So you have always a trade-off. You can do fewer logical qubits with more physical qubits per logical qubit and better errors, or a larger number of logical qubits with bigger errors.
And I guess a follow-up question is that right now you have 99.5 fidelity for qubit gate, and I know there's a lot of laser power already. So what is the path towards going from 995 to 998?
Yeah, you're right. It's higher laser power. So we have a 100-watt laser. For these experiments, we used about 15 watts of the system. So we haven't used the full laser power. The question is what happens to the objective and so on, the lenses through which we send it.
So you mentioned that you're using the error correction as error detection right now.
Mm-hmm.
What are the additional challenges to actually doing the feedback?
Doing the field, very good question. So for error correction, there are 2. You need to image the atoms on a camera, read out the system fast enough from the camera, and then do the decoding, and then in this case, in case of Pauli errors, just store which qubits are wrong. So now we have cameras for the first time that are fast enough to do this on the millisecond time scale. Another question is, as you're imaging the atoms, everything is done optically. You have to make sure that the scattering from these atoms doesn't decohere the qubits, so they need to be spaced on this 100 micron distance or so. We have unpublished data that indicates that at least for these few hundred qubit sizes, this is all working. But of course, as you make the system bigger, there's more scattered light, so you have to worry more about errors, but there are other tricks that we can play to shield data qubits from the scattered light. So it's mainly the fast imaging and then the feedback loop. But because the atoms are so coherent, we don't have to do this very fast. So we are shooting probably for a 1 kilohertz, 1 millisecond error correction cycle, clock cycle in these systems. And that should be sufficient. That's a very good question. It is a limiting factor. That's about 100 microseconds. It doesn't really matter how far we move the atoms. It's most limited by the maximum acceleration we can provide. So for these distances, it's about 100 microseconds. So that's the second slowest time scale. The slowest time scale at the moment is the measurement of the atom, because you need to collect photons. That's at the moment at about a millisecond. We hope to push it down. But ultimately, probably the movement for these systems is a limit. Maybe it can be pushed to a few 10 microseconds. So one of the challenges is maybe to come up with algorithms where you don't have to all the time move the atoms, but maybe do many local gates and then some necessary, non-local gates associated with motion.
Okay.
How do you move some of the atoms without moving the other ones?
So basically we use 2D acousto-optic deflectors that generate certain frequencies. And so basically you can keep certain frequencies the same, and these are the stationary atoms, and then you can change some of the radio frequencies going into your device that correspond to the moving atoms. So basically, each radio frequency that corresponds to a single beam and determines the direction of that beam. So if you change a single frequency, you move a single atom in that trap. So it's a complex, kind of waveform generation procedure that changes some frequencies and keeps others ones constant.
Okay. And to follow up to that, is there a crosstalk from the acousto-optic side of things as you scale the number?
There's some
Saturation effects?
Very good. There's some crosstalks I didn't talk about. We actually do use two kinds of traps. We use spatial light modulators to make static traps, which are very robust. And we only use these acousto-optic modulators to drop them off into the spatial light modulator traps. So yes, acousto-optic deflectors have some crosstalk, so we basically use them only for transporting atoms, but not for storing atoms. So they just pick atoms up and deliver them to another trap. Yeah, that's a very good question. So it turns out that to a very good approximation, maybe I have it here. So this shows the fidelity of the Bell state as the speed of the motion, right? So up to a certain speed of half a meter per second or so, it stays constant. The trapping potential is almost the same for the two hyperfine states because we are very far detuned. And in addition, we do pi pulses during the motion. So the main effect that we see is loss of atoms, not decoherence of the Bell state as we transport the system.
Maybe a very technical one. So like when you're moving, doing this transversal gates and you have these very close atoms together, do you like refresh your SLM for generating those, or do you just always keep those very close with their arm?
So the SLMs are very slow and very static. We don't refresh them. But the SLM pattern is given, and then we use the AODs to drop them there, run the Rydberg gate, and then take them back out.
So they're always there.
They're always there.
Okay, thank you very much.